Good evening, everyone. My name is Gregory Smith from Jet Propulsion Laboratory's Office of Communication and Education, and I am so honored to be your host for tonight's very special edition of our Von Karman series. Tonight, we will be discussing the little Mars helicopter that could, Ingenuity. Designed originally as a technology demonstration that would perform up to 5 experimental flights over a span of 30 days, the Ingenuity helicopter surpassed expectations repeatedly, only recently completing its mission after having logged an incredible 72 flights in its over nearly 3-year mission. Tonight, through the framework of its pilot's favorite flights, we'll learn how Ingenuity's team used resourcefulness and creativity to move beyond the helicopter's initial mission, transforming the rotorcraft from a successful tech demo into an invaluable scouting tool for the Perseverance rover. To help us sift through the multiple questions that we hope to get from all of you watching at home, we have with us one of our very favorite co-hosts from the Mars public engagement team here at JPL, Sarah Marcotte. Hi, Sarah.
Hello, Greg. Great to be here. Listen, we are so excited to take all of your questions. So I will be pulling up questions that we are getting from LinkedIn and X and YouTube. Now, if you're on any of those platforms and you don't see a way to ask a question, try refreshing your browser. A little Q&A place should come up, and we want to hear from you. This is your space program. I also want to point out that after this talk, I bet so many people will have so many questions and want to learn so much more about the Ingenuity helicopter and this historic mission. So I want you to know that we do have a URL that we'll put on screen so that you can follow that link and go to the website and learn more. You can see images from Ingenuity. You can see images of Ingenuity when it was being built. And of course, you can see the ever important flight log, where you can learn all about each one of the flights that Ingenuity took. Thank you.
Thank you, Sarah. For our speakers tonight, we are thrilled to have Ingenuity's 2 lead pilots. First up, allow me to introduce Dr. Havard F, aerodynamics, flight control lead, and chief Ingenuity pilot for flights 1 through 37. Welcome, Havard.
Thank you so much.
Where are you streaming from there? I see some curious equipment behind you.
Yeah, I'm sitting here in our Mars helicopter lab. Behind me, I have some hardware that we use for testing. Every time we do anything on Mars, every time we tell the helicopter to perform some action on Mars, we test it first on some of the equipment behind us just to make sure that we're getting it right.
That's very cool. That makes my office at JPL look like just absolutely nothing. Next, we'll hear from our second guest, Dr. Martin Kaken, who served as guidance and control analyst and pilot for flights 15 through 37 and chief pilot for flights 38 through 72. Hello, Martin.
Hi, Greg. Thank you for having me.
My pleasure. We'll be back to chat with Martin later in the program. Havard, let's begin with you. I'm certain we can't really talk about favorite Ingenuity flights without discussing the historic first flight on April 19th, 2021. Can you give us a brief overview of the monumental challenges that the Ingenuity team faced developing a helicopter for its first flight on Mars?
Yeah, we're going to talk about Flight 1. It was the most important flight that Ingenuity did. But I want to go back a little bit in time and talk about some of the development that led to that flight. Specifically, I want to go back about 10 years to December 2014, which is when we first attempted to fly anything in Mars-like atmospheric conditions. At that time, we didn't know very much about flying on Mars. But we knew one thing, which was that the thin air on Mars would be a real challenge. So the density on Mars, the atmospheric density, is about 1/100th of what it is here on Earth. And so we figured it's, producing enough thrust in that atmosphere, that's going to be a big challenge. And so to convince ourselves and everybody else that this was doable, we built a little test helicopter, which you can see on screen. And it's a very light helicopter. We had a rotor on it that we spun very fast, and we wanted to show that this could fly. And if you play that video, you will see that as far as producing thrust and getting off the ground, it did the job. But as we started flying this, we instantly noticed that we couldn't keep the helicopter under control because it wouldn't respond in the same way as a helicopter would on Earth. You didn't get the kind of clean, crisp response, rather it would sloppy and oscillatory. And so the experiment ended very abruptly, as you can see there. And it was a lesson for us because we realized this problem is so much bigger. It's not just about producing thrust. We really got to go to work here and learn how do we build helicopters that are actually flyable and controllable on Mars. So that brought us into a phase of this project that was really laser focused on that. And one of the great resources we had in that work, if you go to the next slide, you can see what we call the JPL 25-foot space simulator. That's a big facility that we have here at JPL where we test pretty much all our spacecraft. Mostly they go in for a few days or a few weeks, but the Mars Helicopter Project, we spent more time there than any other mission in JPL's history. Months on end where we used this space for aerodynamic testing and eventually flight testing. So if you go to the next slide, you can see some of the creativity that we had to use in order to understand how the helicopter behaved in this atmosphere. This is what we call our poor man's wind tunnel. So what it is, it's an arm that's holding the helicopter upside down, and the helicopter is swinging back and forth. And the reason for that is we wanted to generate a little bit of airflow over the rotors. And that way we could measure with force torque sensors the response to that edgewise flow over the rotors. And that was one way for us to learn about how it responded in that environment. Now, if you go to the next slide, you'll see that later in the project, we got a little bit more sophisticated about how to generate airflow of wind for the helicopter. This is something we called the wind wall. We built this by buying up all of the CPU fans we could find anywhere. There's about 900 identical CPU fans here, the kind of things you find in a desktop computer. We put them all in a big array and used it to blast air at the helicopter. If you go to the next slide, you can see what the helicopter looked like in front of that wind wall. It's, again, upside down, thrusting downwards, and it's mounted to what we call a gimbal. Gimbal allows the helicopter to rotate, but it can't go anywhere. So that allows us to actuate it to perform what we call frequency sweeps, for example, where it's basically oscillating back and forth at different frequencies without risking it going off and crashing into a wall. Now, if you go to the next slide, you'll see one of the baby steps towards flying a helicopter. Here, the helicopter is hanging from a string. In fact, it's a piece of a fishing line that's hanging, it's suspended from. And you can also see, if you look very carefully, that there are fishing lines hanging from the legs as well. And that's a way for us to try to fly the helicopter just a little bit. We could come off just a few centimeters and fly, but if something goes wrong, those tethers are there to catch it. And another reason why we have the tether on top is it's helping offload part of the gravity, because the helicopter is heavier on Earth than it is on Mars. So it's got to have a little bit of help when you're testing it on Earth, so it's pulling up with a force to cancel some of the gravity. One of the kind of weird practical aspects of this kind of thing is just we're putting this piece of hardware, this is all we have, and we're putting a piece of fishing line. How you make sure that it's safe to do that? You would not believe the amount of time that we spent debating the knots that we used to attach this helicopter. We spent days, maybe weeks, debating and testing different knots to be absolutely sure that we got that right. Those are just some, the weird practicalities of conducting a test campaign like this. If you go on to the next slide, you will see another type of testing that we did sometimes where we are tricking the helicopter into thinking it's flying. We have a navigation system on board the helicopter that's looking down on the ground and it's trying to navigate. And we can trick that system into thinking that the helicopter is flying by carrying it around in the manner that you see in this image. Now, eventually, of course, we got around to doing more flight testing. So if you go to the next slide, you will see a video of the first fully controlled free flight that we did with a helicopter in Martian atmosphere. And this shows what a difference it makes to really take the time to figure out what you're doing. This was the proof that we all needed that this is actually possible. So we could go on and actually build a full-fledged helicopter to survive on Mars.
That must have been such an incredible moment for the team.
It was a nerve-wracking moment because we really couldn't afford anything to go wrong at that point. So we were all, holding hands and just biting our nails and and when we counted down to that takeoff. But yeah, it was a big moment when it flew.
Who'd have thought the future of a NASA mission could rest on a carefully tied piece of fishing line? It's just incredible. What an incredible creative team. Let's jump ahead many, many months, Havard. Perseverance has successfully landed on Mars with Ingenuity sort of hitching a ride on its belly, if you will. On February 18th, 2021, did the team already have a definitive first flight location planned? How did you all decide on what eventually became known as Wright Brothers Field?
Yeah, so that was my job when that rover landed on Mars. We didn't know where it was going to land. So my job, starting that very evening when the rover landed, was to lead a team to figure out where do we put the helicopter down so we can fly it. And at that time, we worked what's called Mars time. That means that our workday followed the Martian day rather than Earth day. So it moved around by about an hour every day. So I'd find myself in the middle of the night at 2, 3 in the morning, sitting with a team of 5 or 10 people discussing single rocks, pebbles the size of a few centimeters on a planet that's hundreds of millions of miles away. And there's just something very surreal about doing that kind of work. So if you go to the next image, you'll see what eventually we dedicated as Wright Brothers Field. This is a kind of data products we were looking at. This is an overhead view taken by the rover of that area, and it's color-coded with different obstacles that we found in that field. So these obstacles are high slopes and rocks, and the colors indicate how severe those obstacles are. And some of them we are quite worried about. And if you go to the next slide, you'll see an inset that tells you, that shows the larger rocks that we were worried about, the kinds of obstacles that the helicopter we'd rather not come into contact with the helicopter. If you go to the next slide, you'll see another tool that we use a lot, which is simulation. This is a simulation of what a flight could look like in Wright Brothers Field. And as it turns out, it's a pretty good representation of what the eventual flight did end up looking like as well. And this has a good representation of of all the rocks in that space that we flew in.
Incredible. What was it like to be in the room when the first flight successfully took off and landed safely?
It was tense. At that point, personally, I'd spent about 8 years of my life on this, both at work and a lot of my spare time too. And it comes down to one single moment in time where either it's all validated and you get to celebrate, or it falls apart. And maybe it was a good effort, but it still failed. And the difference between those two things is pretty large. And I also had the responsibility or the privilege of looking at the data and declaring, yes, we flew, or if not, then we had a whole all sorts of thoughts in my head about what would that look like. Thankfully, it was yes, we flew, and I think we have a video queued up here that shows a little bit about what that was like.
This is Downlink. We are beginning to see data products.
Rotor motors appear healthy. All actuators appear healthy.
It does is reporting having performed spin-up, takeoff, climb, hover, descent, landing, touchdown, and spin down. Altimeter data confirms that Ingenuity has performed its first flight of a powered aircraft on another planet.
That video gets me every time. It's incredible. You're in the room, and if it's hard for the audience to tell, you're the person who is actually giving the data as you're receiving it. You seem very sedate almost. Were you a little bit in shock?
Almost. You know, before that moment, there were so many thoughts going through my head about all the things that could go wrong, and some of them are like bizarre, like what if we got gravity on Mars wrong, you know, those kinds of things, which is absurd, but you can't help having those kinds of weird thoughts. And then when it flew, it was just such a relief. I kind of just sat there, and in fact somebody had to nudge me and like show the images, you know, the images from the camera, like they had to remind me to do it, you know. So yeah. Whereas a lot of, you know, people were jumping up and down, clapping. I kind of just sat there for a moment.
It's fantastic. It's a real testament to how much you were invested in the moment. So let's jump ahead again. After the team successfully completed its first 5 flights as a technology demonstration, I imagine you all asked yourselves, what's next? So which of the successive flights pushed the limits of the helicopter and led to it being ultimately used as a scouting instrument for the Perseverance rover?
Yeah, so if you go to the next slide here, you'll see a satellite image with Wright Brothers Field drawn on it. And the big oval there, that's the area that we dedicated as our experimental test flight area. Because this mission was supposed to consist of flight 1 and up to 4 more flights within that area. But then, you know, almost as soon as we flew, people, you know, realized this is a real, you know, flying machine that we have on Mars. You know, it's not just a toy. You know, let's use this. And so we were told, as a surprise, you know, you get to continue. But now, you don't get to just hang around in this very benign area that you found. You got to go explore Mars. You got to keep up with the rover, which is going to go on and do its thing. And so we started, you know, baby stepping our way. And if you go to the next slide, you'll see our first few flights as we ventured out of this area. And in those few flights, 4, 5, 6, 7, 8, if you move ahead here, you'll see what those flights look like. Go on a few more, go to flight 8 here, and you'll see these are flights over still very benign terrain. It's flat, there are places to land. But then we got to flight 8, we had a kind of big decision ahead of us. If you go one more here, you'll see where the rover was planning to drive at that point. It was going around this big area called Sita. It couldn't drive across here, so it was going to spend a lot of time driving around there. And we realized it would be tough for us to fly there because there weren't that many good places to land. And it also would be kind of crowded, you know, with us and the rover there. And so we decided, why don't we go for it here and really show what helicopters are for and just go right across, take a shortcut. If you go to the next slide here, you'll see what that planned flight 9 looked like. And so we decided we're going to go for it. It's a huge challenge because of the terrain. The navigation system was not designed for this kind of terrain. It was a much longer flight, both in distance and time that we've done this far. But we saw this opportunity where we had this large landing field, a potential airfield on the other side. So we decided to go for it, and it was successful. And to me, that is the moment where Ingenuity broke out and became a real Martian explorer, because now we were ahead of the rover. We could put Ingenuity to use as a scout on behalf of scientists and the rover drivers, we went and did actual scouting at that point. And so to me, that is the flight that I think really stretched the limits early in the mission.
Incredible. I'm certain at this point, our co-host, Sarah Marcotte, must have a bevy of questions for you, Havard. But before we do that, I just want to make sure that I know that you have a video of that actual flight, and I would love to show that video.
Yeah, go ahead here. So you'll see a couple of images here. Yeah, this is a sequence of images taken by the helicopter itself, its navigation camera. This is a camera the helicopter uses to figure out where it is as it's flying. It uses that together with a couple of other sensors. A laser rangefinder measures distance to the ground, and an inertial measurement unit that measures the accelerations and the angular rates of the helicopter. So by fusing all of that information, it figures out where it is. So this is the view that the helicopter has as it's flying.
It's incredible. And we also have a couple stills of what the rover saw and what, is that correct, of this area? If we go back a couple slides?
Yeah, I've got a couple of images here. You can see a picture of what the rover saw. That's what that is. And then you can see almost the same view from the helicopter's point of view in the air prior to crossing this region that we call CETA.
Fantastic. I would love to have Sarah ask a couple audience questions if we have them. Sarah Marcotte, what do you have for Havard?
So we have so many audience questions, and I'm going to tell you I'm struggling a little bit because there's a lot of good ones. So people are really interested in things like the design, and then also how your designs, what you learned when these designs went from the test chamber directly to Mars. So the first one I'm going to ask is from Lightning Rod on YouTube. Lightning Rod is asking, how did your flight calculations compare to the real world on Mars? What was unexpected, and what did you get exactly right?
You know, I expected that we'd get to Mars and it would fly, but we'd be left with so many questions, so many oddities in the data that we'd have to go investigate. And so the biggest surprise to me was when we got that data and we started looking at it, it looked like our simulations. It looked so similar. It felt like we'd been doing these kinds of flights for years. And so in a sense, the biggest surprise to me is just how well we were able to predict it, which is, it's the best kind of surprise because it really validates the tools that you've spent years developing. So of course, as we went on with the mission, there were things that we didn't expect as well, but up front, that was the biggest surprise for me, is just how well things lined up.
Excellent. Well, that must feel really good. Okay, the next two, well, actually, I'm asking one question, but I'm kind of combining two questions because there's so much interest in sort of the design and design process. So I'm kind of combining a question from FinKip Girl and Pete Edwards. Both of these are from YouTube. I'll sort of summarize it. You know, with hindsight, so now that you've been flying the helicopter, what design attributes would you change in the current design? Were there any issues that you would improve or change?
There are a few minor things. So to give you an example, what we started seeing after a while, in that camera view that you saw, you started seeing little pieces of dirt or dust that was moving around and sitting on the inside of the glass sometimes. And it's just one of those things because that glass is the lowest point inside our electronics box. And so that dirt didn't have anywhere else to go. And so that's like a minor little thing, but it's an example of the kind of things you figure out, okay, we'd do that a little bit differently. Then there are just technology improvements that we would take advantage of. If we went, and did another helicopter, technology has advanced since we built this one. And for example, having a higher resolution camera, that's the kind of thing that I would like to see for a future helicopter, just because it allows us to better resolve the detailed features on the surface as we're navigating.
All right. Well, thank you, Sarah and Havard, and everyone watching. Fantastic questions so far. Sarah, thank you for choosing some gems in there. And we will bring Havard back at the end of the show to answer some future questions. All right, so keep them coming. Right now, let's bring in Dr. Martin Kakin into the conversation. Martin, welcome back. You were on Ingenuity's pilot team since Flight 15 and took over as chief pilot from Flight 38 through its end of mission at Flight 72. Across that journey, is there one flight you want to highlight?
It's a really tough question, Greg. I mean, again, we flew for nearly 3 years on Mars. So, looking at this first chart I have pulled up, again, you can see where we went from the corner. Can you go, I guess, back a couple of slides to slide 20? Here we go. Thank you. I mean, again, here's the journey that we took, right? The inset of Zeta was what Havard was just talking about, starting from the star in the top right corner at Wright Brothers Field. Multiple Zeta crossings, the journey across 3 forks, and, this trip up the Delta region, in total over 10 miles and 72 flights. Each flight is truly a milestone and an incremental step on this epic journey. But there are 3 cases here I would like to highlight to try and show the type of impacts that Ingenuity had. So first here in Flight 26, we had this great opportunity to image the entry, descent, and landing back shell and parachute. So this helps the rover decelerate from interplanetary speeds to land safely on Mars. Can we go to the next chart, 22 here? Yeah, so here we are in that image. And so again, this was really cool, able to fly behind. And again, this is what helps the vehicle actually land safely on Mars. And by taking these pictures, the engineering structures team was able to analyze this and basically do a destructive impact analysis to see, what was overly designed, what was under-designed, and the next Mars mission is going to be better because of this. So, really exciting to see the type of engineering impact we can have. And then sometimes we get to have, really cool science impact. In this next example for Flight 52, when we landed, on the next chart, you see that we saw these vesicular rock. So we kind of found this unexpected geological unit. So we kind of expected to land here because it was free of large rocks. But we found this specific vesicular rock behavior, and the scientists got really excited by this. And you can see for the rover route on the right, the rover was originally planning on driving right through this region, but in the end did this large diversion north and south of its route based on the imagery that we were able to provide to the team. So again, really cool how we can impact science that was done by the project as a whole. And the last example I wanted to bring up here on the next chart is kind of just as a lot of the fun of flying a helicopter on Mars. There's moments when you kind of just get to be a National Geographic photographer and really try and leverage this cool vehicle that we have on Mars to, impact the community and really try and engage with the public in an example like this. So we didn't know exactly where the rover was going to be. So you see our flight plan on the bottom left had some zigzags and multiple images that we tried to take. And we're rewarded with this super unique perspective of Perseverance doing science along the edge of Belva Crater. You can see the tracks along to get there, and our shadow there in the front. So a little bit of a team photo.
I am understanding your dilemma in choosing, but it's such an embarrassment of riches in terms of engineering and scientific discovery. It couldn't have all been highlights, right? So is there any, was there a notable challenge to overcome during its long journey?
Yeah, I mean, there were multiple, but I guess there's one that I would love to bring up, which is Flight 40, which was, kind of similar to Flight 9, just a major kind of departure from what we had done previously. So this is the first time we flew up into that Delta region from the map before. So we were kind of leaving the 3 forks. We were leaving this crater floor. And again, this really just presented a lot of new challenges. The Delta region was much steeper terrain, much hillier. There were a lot of rocks. We had to start accepting rocks in our airfields, which is something we had never really done before. And so these new challenges really required new tools. And so we actually got a lot of the team back together, developed a new software update, and pushed that up to Mars. And notably what this did is it started implementing a hazard avoidance algorithm. And so previously we would get to the end of the flight, we'd come to our final waypoint, and we would go and we'd land. Now we get to the final waypoint and we actually survey the ground and try and find what is the best place that we can land, and we'll do a small diversion over to that place and land. And so that was really this kind of key capability that we needed. And so really to kind of give you some perspective on why, you can go to the next chart. And we can see what our airfields used to look like. So on the left, we see the Three Forks region. This is just this huge, flat, I mean, it's literally almost a gigantic basketball field or football field. I mean, it's very flat. This is great terrain, can land anywhere. On the right, we have Seta, definitely a much smaller airfield, but still nothing here is more challenging than what we saw at Wright Brothers Field. Whereas for Flight 40 in the next chart, you see the airfield that we had to land in as scouted here by the rover. So now we have, discrete sand ripples. We have a lot of small rocks that are not really hazards, but then we do have several large rocks that really would be a problem for Ingenuity if we landed there. And not only that, we have to land at this airfield after climbing the largest hill we've ever climbed, 50-foot climb. So again, not something too bad for you and me, but for this little helicopter, I mean, this was just a monumental change in what we had done before. So again, a lot of simulation led up to this point, a couple of preliminary flights that were tested in a low-risk way to kind of test these capabilities. But when we were confident that it all was going to work, it was time to fly. So again, we have another great little video here to show of the nav camera. So this is, again, pointed down from the helicopter. We're kind of leaving the sand ripples of the Three Forks region and here kind of going up the Delta foothills. And importantly, here's the divert we do and land very safely here between these ripples. And so on the next chart...
I'm so sorry to interrupt you. Am I right in that we just saw the tracks of the rover in that? That's an incredible video.
Yeah, it's a lot of fun. I mean, like Havard mentioned earlier, you're operating this vehicle that's hundreds of millions of miles away, right? And so when you sit there and you're like, I want to take a picture of that, it's this really kind of just, you're really just reaching out there and clicking and taking a picture, and then you're getting that back down. I mean, it really is quite an experience to operate.
Amazing. I know you had one more slide that you want to compare to that video.
Yeah, just to kind of highlight the divert we did at the end. So again, on the left there, we started at the center of the image, and we kind of did a divert of about 5 meters up to the star there on the left side. And so kind of picked this really nice bland spot between these two ripples where, again, the vehicle thought it was safest to land. So this was really the technology and the capability we needed to continue to be an operational asset as we really started to go into this much more difficult terrain.
So Martin, what other flights pushed the team's resourcefulness and why?
Well, right after we had proven in Flight 40 here that we could handle this type of terrain, we were requested to, basically pedal to the metal up the Martian terrain. And so actually Flight 42 through 46, or excuse me, 43 through 46 is the case I want to discuss because it really is, I think, a record that gets overlooked. So in this next chart here, we managed to get up this Delta Valley in 10 sols and accomplished 4 flights in that time, going a mile, over 100 feet of climb. And this is just so impressive when you realize that typically we would fly once in 10 sols. A sol is a Martian day, so again, very similar to an Earth day. But we would typically fly maybe once per 10, maybe even 14 sols. And a lot of times even that is a challenge. So to get 4 flights into that same period, truly was, I think, a really impressive accomplishment. part of this happened because the terrain really forced the heli and the rover along the same path. So, as Havard discussed with Seta, we really were able to leverage our mobility to kind of take the alternative route. Here, that wasn't really an option for us because there was no safe place to land. We had to kind of take the same route as the rover. So again, kind of forced in the same spot was really difficult to operate in these kind of proximity operations. And so like kind of positionally, if this is a game of leapfrog, as we're both trying to work up the valley here, like it's a big frog and we're a very small frog. So it's really easy for it to pass us, but it's really hard for us to pass the rover, right? We don't want to fly too close to the rover just in case something goes wrong. But the rover can drive right past us, with a lot of confidence that everything's going to be fine. And so, if it's this game of leapfrog, we're going to lose. And so we really had to make this a race. We had to get ahead and we had to stay ahead. And that's really what kind of drove us on this schedule. So to kind of hammer this home, in the next chart, you'll see a telecom map. And so basically what this is a prediction of how well we're going to be able to communicate with the rover. So if the helicopter was landed at the star there, then if the rover was anywhere in one of those green regions, that's full bars on your cell phone, we can communicate. Red means you got 1 bar, maybe you can communicate. And outside of that, you can't communicate with the rover at all. And so if the rover was ahead of us and it made this turn to the west before us, we would have lost comm with the rover, and the rover wasn't coming back. It was an end of mission scenario to get passed by the rover. And so, really forced us to go fast, forced us to stay ahead. And the challenge as well there is that there's only so far you can get ahead. There's a number of flights where we did execute a flight like this and flew out of comms range with the rover. And so kind of mid-flight, you lose communications. The helicopter still is autonomous. It will take itself to that destination and land. It doesn't need comms. But us on the ground, we like to get that data down. And so it can be very difficult to kind of assess that data and add more operational delay, all the more kind of challenge to this period. But again, we kind of know this was not the end of the journey. On the next chart, we know that the helicopter, this little helicopter that could beat the rover up through this journey, and was really accomplished, thanks to a really well-oiled operational team. At this point, we did have, 40-plus flights of experience underneath us that really made things go really effectively. Again, this new software we just uploaded, really helpful to get us through. And a lot of extremely diligent flight planning on behalf of our GNC pilot team, of doing a lot of simulations. On this next chart, you'll see an example of one of the simulated flights here. So for every flight, we run hundreds of flights on different variations to find the optimal flight. And we did that all the way up the channel here, as you can see. And so just constantly we're leveraging our ability to do, use simulation to kind of build confidence and fly on Mars. Proceed a couple more. And then, ultimately though, this just shows that, the GNC side of things, of our pilot team, of planning our flights, but, there really is an entire ops team here working around the clock for this, 6 a.m. shifts, there were 11 p.m. shifts, weekend shifts, a lot of dedication to get this done. So ultimately, flying a helicopter on Mars takes a village. So the next slide, we just wanted to show the team. This is at our 2-year anniversary on Mars, and wanted to thank the entire team for their hard work, their dedication, and all the fun we've had up to this point. And definitely also want to thank the public and everyone's engagement, with our Ingenuity project. Really kind of keeps us going to this point. So thank you so much.
Thank you. Those smiles in that photo are really well earned. Martin, you and Havard and your team have accomplished, what you've accomplished is historic and extraordinary. And thanks to all of you for inspiring so many of us mere Earthlings back here on Earth. Speaking of inspiring Earthlings, I bet Sarah is inundated with questions from our viewing audience. Sarah, what do you have for Martin?
I am, and it's kind of neat because people sometimes give their location when they ask a question, and we've had a question from Chile, we've had a question from Texas, so they're coming in from all over the place.
Fantastic.
But in terms of platform, this one is from X. So Filigrew on X is asking Martin, the decisions when you're going to send like commands to the helicopter, do you simulate them in sort of any sort of simulated environment before sending them to the helicopter?
Extensively. So, we have a computer simulation environment that we do a lot of tests in, and so that was kind of what I showed previously, showing kind of the trajectories going up Mars. But again, all that is in software. So we also have our hardware test beds. One of those is where Havard's located. So, we take those sequences and, vet them through a lot of different channels to make sure that we have high confidence before actually transmitting them to Mars.
Excellent, thank you. And another question from YouTube, Max Headroom on YouTube, wants to know how was Ingenuity used to help Perseverance's operations?
Yeah, I mean, it was, again, we somewhat started to highlight it, but we often operated in advance of the rover. And so, sometimes there was curiosity from the science team of, like, what is that rock feature over there? Like, is it worth driving this rover over there? And so, it takes a lot of time and scheduling for the rover, and for us to kind of just sit there and be able to really quickly pop over, grab an image, and come back allows the science team to decide, is that an investment they want to make with the rover? And also, we had a big impact on the rover drive planners, right? So that's basically our equivalent on the rover. When you kind of fly through an area that's particularly maybe really rocky, or the team knows it's going to be a challenge for the rover, the imagery we provided was significantly better than the satellite imagery they have. And so, again, kind of being able to provide higher resolution images really did be able to help the team, better plan the route and, get to its destination in an efficient manner.
Well, thank you, Martin. Let's bring Havard back into the conversation to answer some joint questions. Sarah, do you have any good questions from our audience that both of our excellent speakers might be able to answer?
Sure. The next one might be along in Havard's wheelhouse here, rotor house, sorry. Let's see, because I thought this was very interesting. This is from Francisco Barra on YouTube, wondering about, was it an option to test a helicopter on Earth at 60,000 feet? Would that kind of test been valuable despite the difference in gravity?
It could have been. In the end, it's tricky, right? Because you have to get up to 60,000 feet in the first place. And then gravity is a big factor here, right? Because that first helicopter that I showed a video of, that actually flew itself in Earth gravity, but Martian atmosphere. But in order to do that, we had to get rid of everything that wasn't strictly needed in order to prove flight. So it didn't have its own batteries, it didn't have a solar panel, it didn't have telecom or even a computer. So all of that was fed through a tether extending from the ground. Of course, you can't do that at 60,000 feet. And so the practicalities of it are what led us to conclude that that was not a path that we should pursue. Plus, it's more than 60,000 feet. It's more like 100,000 feet.
100,000 feet, okay. So it's up there. It's where the air would be very thin for anything to fly. So flying up there would be even more challenging, but you did it on Mars. Next question is for Martin. Silver Show on X is asking, what were the challenges of working in close proximity to the rover? Was it safety?
Yeah, I mean, the number one concern is, let's not take this small, tech demo turned operational, operational tech demo effectively, and harm the rover in any way, shape, or form, right? We were a, do no harm type of project. We could, take a lot of great pictures, have a lot of great benefit, but, by no means could we interfere with the rover. So there was just a lot of safety and a lot of precaution that came down to that. There was, both concerns of, the rover drives autonomously as well. It does a lot of auto navigation. And there was uncertainty on whether the rover's auto nav would recognize Ingenuity, and particularly all the blades as it went out. And so what happened if the rover drove over Ingenuity, or broke a blade and cut a wire, or stuff like that. So yeah, there was a lot of concerns of that, and so that really kind of drove the difficulty in that time.
Okay, so so I want to ask 2 more questions. We'll get them in because I know what I want to end with. So this one is from Tim Miller on YouTube, and Tim is asking, so what did we learn about flying on Mars with the weather variables and the air temperature, and will that help you in the future?
Is that a question for me or Martin?
Oh, I'm gonna stay on Martin because I'm going to you for the last.
Sure.
Sorry about that.
Well, I mean, a lot of the, the last year of our mission, you can see some of our blog posts about it. We really were trying to push the limits, flying faster, flying higher. We even did a system identification campaign to not just, see how, if we could fly faster, but knowing how we could fly faster, and, really kind of trying to do some of this testing that we saw videos of earlier on Mars. So, I'd say we learned just a plethora of information. We're going to be digging through this for years. And so, we're already planning the next helicopters for Mars, and all this data is getting recirculated back into that to make the next design better. So definitely a ton that we've learned, and we'll keep learning truly for years.
Yeah, so that really is what many of these questions are going towards, is that people are not satisfied with just this one helicopter. Clearly, the public all throughout the world really wants to see more rotorcraft and future uses of this amazing technology. So, Havard, can you tell us about, are there plans perhaps on other planets or other places where we might use helicopters?
So our dream is, having lots of helicopters exploring Mars in the future. We think this is a great way to get around Mars. It's a new way to get around Mars. And so we want to see it used that way. And we think it has a ton of potential. So we're working right now on concepts for much larger and more capable helicopters than Ingenuity. We're talking helicopters that weigh tens of kilograms instead of the 1.8 that Ingenuity weighed. And that could, have much longer range, can fly faster, that can carry large payloads, and several kilograms of payloads. And we think that has a ton of potential. As far as other planets, there is a current effort underway, a current mission that is being developed for a flight on Titan. And so this is not a planet, but a moon, but it has an atmosphere. Very different atmosphere from Mars, I should say. They have the opposite kind of challenge where the air is much thicker. It's much heavier than on Earth. So it's different in a different way. But we try to help out with the knowledge that we've gathered as part of flying one helicopter in outer space and feeding the lessons learned from that to the people working on that mission.
Excellent, excellent. I think, is that all the time we have for questions, Greg? How are we doing?
We have time for one more.
I love it. Excellent. I'm so glad, Havard, that you brought up Dragonfly, because we had a whole bunch of Dragonfly questions. So people are on to the Dragonfly thing, and they're wondering if things that we learn with this mission are going to be helping with Dragonfly. And Havard, you just got a question about, I think somebody wasn't here in the beginning, about why you have to be wearing that white suit in that space that you're in. I wanted you to talk about your space.
Yeah, so this is a so-called ESD protected area. So ESD is electrostatic discharge. So if you imagine you're walking around at home, in your socks, and you touch a door handle or something, you can feel a little spark. Well, those kinds of sparks we don't want anywhere near our sensitive electronics. And you could have discharge that are, at much lower level where you don't even feel it, but still it could be damaging to electronics. and we don't want to damage our electronics and send them out into space and then have issues with them afterwards. And similar in this area, the equipment behind me is not going to space, but we still have to keep it safe. And so that's why we take certain precautions. We're grounded when we work near the electronics, and we also wear clothes that minimize the chance of any kind of electrostatic discharge events.
Excellent, thank you. So just another reminder of a special place that you work in and special work that both of you do, operating helicopters on other planets.
Well, my friends, I'm afraid that is all the time we have tonight. Thank you, Sarah. I'd like to thank our special guests, Havard and Martin, for sharing your expertise and passion with us all. And also thank you to the many members of the Ingenuity team who generously gave me their time to help me prepare for this talk. To my wonderful co-host, Sarah, I can't thank you enough for being there, for sifting through all of those fantastic questions. Our amazing social media team behind the scenes, our incredible audiovisual production team, and of course, to all of you watching at home for being passionate about what we do here at NASA JPL. And for tuning in tonight. We can't thank you enough. Be sure to join us next month as we celebrate Earth Day with a talk about JPL's newest Earth orbiter, SWAT. And remember, this is your space program. So be involved, stay curious, and yay science. Good night, everyone.